4. Securing your server with a firewall, Part 1. Security is one of those things that's best done in layers. Security in depth, we call it. So on any given corporate network, you will find a firewall appliance separating the internet from the demilitarized zone, DMZ, where your internet-facing servers are kept. You will also find a firewall appliance between the DMZ and the internal LAN, and firewall software installed on each individual server and client. We want to make it as tough as possible for intruders to reach the final destinations within our networks. Interestingly though, of all the major Linux distros, only the SUSE distros and the Red Hat type distros come with a firewall already set up and enabled. Newer versions of Ubuntu come with a pre-configured firewall, but you need to activate it by running a couple of simple commands. Since the focus of this book is on hardening our Linux servers, we'll focus this chapter on that last level of defense, the firewalls on our servers and clients. We'll cover both of the command line netfilter interfaces, which are IP tables and NF tables. In this chapter, we'll cover the following topics: an overview of Linux firewall, an overview of IP tables, an overview of NF tables. In the next chapter, we'll cover UFW and firewall, which are handy frontends for IP tables and NF tables. Technical requirements. The code files for this chapter are available here. An overview of the Linux firewall. In a typical business setting, especially large enterprises, you may encounter various types of firewalls in various places that can provide various types of functionality. Here are some examples. Edge services that separate the internet from an internal network translate routable public IP addresses to non-routable private IP addresses. They can also provide various types of access control to keep out unauthorized people, by also providing various types of packet inspection services that can help prevent attacks on the internal network, keep up malware, and prevent the leakage of sensitive information from the internal network to the internet. Large enterprise networks are normally divided into subnetworks or subnets, with each corporate department having a subnet to call its own. Best practice dictates separating the subnets with firewalls. This helps ensure that only authorized personnel can access any given subnet. And of course, you also have firewalls running on the individual servers and workstations. By providing a form of access control, they can help prevent an intruder who has compromised one machine from performing a lateral movement to another machine on the network. They can be also configured to prevent certain types of port scanning and denial of service, DOS attacks. For the first two items in the preceding list, you will likely see dedicated firewall appliances and terms of firewall administrators taking care of them. The third item in the list is where you, the Linux professional, come into the picture. In this chapter and the next, we'll look at the firewall technologies that come packaged with your Linux server and Linux workstation distros. The name of this Linux firewall is netfilter. This netfilter code is compiled into the Linux kernel and is what performs the actual packet filtering. There's no way for human users to directly interface with netfilter, which means that we need some sort of helper program to interface with netfilter for us. There have been 3 helper programs, which are IP chains. This was the first one and was part of the Linux kernel up through kernel version 2.4. It's now ancient history, so we won't say any more about it. IP tables. This replaced IP chains in Linux kernel version 2.6. It's still used in a lot of Linux distros, but it's rapidly disappearing. NF tables. This is the new kid on the block, and is rapidly replacing IP tables. As we'll see later, it has a lot of advantages over the older IP tables. All 3 of these helper programs do 2 things for us. They provide a command line interface for human users. They take the commands that human users input and inject them into netfilter. To make things even more interesting, we also have helper programs for our helper programs. The uncomplicated firewall, UFW, was created by Ubuntu developers and is a front-end for either IP tables or NF tables. Ubuntu comes with UF already installed, and you can install UFW yourself on Debian and all the Debian type distros. On the Red Hat side, we have Firewall D, which is also a front-end for either IP tables or NF tables. Note that firewall.d is installed and active by default on all Red Hat type distros, as well as the SUSE distros. It's available as an option for Ubuntu and Debian. Both UFW and firewall.d can vastly simplify the process of setting up a proper firewall. Still though, it's sometimes helpful to know how to work with either bare IP tables or bare NF tables. So let's begin by looking at IP tables. An overview of IP tables. As I mentioned, IP tables is one of two command line utilities that we can currently use to directly manage NetFilter. It was originally introduced as a feature of Linux kernel version 2.6, so it's been around for a long time. With IP tables, you do have a few advantages. It's been around long enough that most Linux admins already know how to use it. It's easy to use IP table commands and shell script to create your own custom firewall configuration. It has great flexibility, and you can use it to set up a single port filter, a router, or a virtual private network. It still comes pre-installed with some Linux distros, although it's rapidly getting replaced by NF tables. It's very well documented and has free of charge book-length tutorials available on the internet. However, as you might know, there are also a few disadvantages. IPv4 and IPv6 each require their own special implementation of IP tables. So, if your organization still needs to run IPv4 while in the process of migrating to IPv6, you'll have to configure two firewalls on each server and run a separate daemon for each. One for IPv4, the other for IPv6. If you need to do MAC bridging, that requires EB tables, which is the third component of IP tables, with its own unique syntax. ARP tables, the fourth component of IP tables, also requires its own daemon and syntax. Whenever you add a rule to running IP tables firewall, the entire IP rule set has to be reloaded, which can have an impact on all performance. Until recently, just plain IP tables was the default firewall manager on every Linux distro. It still is on some distros, but Red Hat Enterprise Linux 7 and all of its offspring now use the new firewall.d as an easy-to-use front-end for configuring IP table rules. Ubuntu comes with Uncomplicated Firewall, UFW, which is also an easy-to-use front-end for IP tables in all Ubuntu versions up to 20.04. In this chapter, we'll discuss setting up IP tables firewall rules for both IPv4 and IPv6, mastering the basics of IP tables. IP tables consist of 5 tables of rules, each with its own distinct purpose. A filter table. For basic protection of our servers and clients, this might be the only table that we use. Network address translation, NAT table. NAT is used to connect the public internet to private networks. Mangle table. This is used to alter network packets as they go through the firewall. Raw table. This is for packets that don't require connection tracking. Security table. This security table is only used for systems that have SE Linux installed. Since we're currently only interested in basic host protection, we'll only look at the filter table for the time being. In a few moments, I'll show you a couple of fancy tricks that we can do with an angle table. Each table consists of chains of rules, and the filter table consists of an input, forward, and output chains. Let's look at this on an Ubuntu 20.04 virtual machine. Ubuntu 20.04 LTS comes with IP tables, and Ubuntu 22.04 comes with NF tables. However, even if you're running Ubuntu 22.04 or newer, you'll still want to learn how to work with IP table commands. The first reason is that Ubuntu 22.04 includes a cool feature that automatically translates IP table commands to NF table commands. This allows you to use any IP table scripts that you might already have without worrying about converting them to NF tables format. The second reason is that once we start talking about Ubuntu's Uncomplicated Firewall, UFW, you'll see that you still need to know IP table commands in order to configure it, regardless of which Ubuntu version that you're using. First, let's look at our current configuration by using the sudo iptables-l command. Sudo iptables-l. Remember that we said that you need a separate component of IP tables to label IPv6. Here, we'll use the sudo ip6tables-l commands. Sudo ip6tables-l. In both cases, you can see that there are no rules and that the machine is wide open. Understand that Ubuntu actually does come with a pre-configured uncomplicated firewall, and you also see some output that is specific to it, but we'll ignore that for the time being so that we can work directly with IP tables. We'll start by creating a rule that will allow us to pass incoming packets from servers that our host has requested a connection to. sudo IP tables -a input -m contract --ct state established related -j accept. Here's the breakdown of this command. -a input. -a places a rule at the end of the specified chain, which in this case is the input chain. We would have used -i had we wanted to place the rule at the beginning of the chain. -m. This calls in an IP tables module. In this case, we're calling in the contract module to track connection states. This module allows IP tables to determine whether a client has made a connection to another machine, for example. -ct state. The CT state, or connection state, portion of our rule is looking for two things. First, it's looking for a connection that the client established with the server. Then, it looks for the related connection that's coming back from the server in order to allow it to connect to the client. So, if a user wants to use a web browser to connect to a website, this rule will allow packets from the web server to pass through the firewall to get to the user's browser. -j. This stands for jump. Rules jump to a specific target, which in this case is accept. Please don't ask me who came up with this terminology. So this rule will accept packets that have been returned from a server to which the client has requested a connection. Our new rule set will looks like this. Sudo IP tables -l. Next, we'll open up port 22 so that we can connect through secure shell. Sudo IP tables -a input -p tcp -d port ssh -j accept. Here's the breakdown. -a input. As before, we want to place this rule at the end of the input chain with -a. -p tcp. -p indicates the protocol that this rule affects. This rule affects the TCP protocol, of which secure shell is a part. -d port ssh. When an option name consists of more than one letter, we need to precede it with two dashes instead of just one. The -d port option specifies the destination port on which we want this rule to operate. Note that we could have also listed this portion of the rule as /d port 22, since 22 is the number of the SSH port. -j accept. If we put this all together with -j accept, then we have a rule that allows all the machines to connect to this one through secure shell. Now, let's say that we want this machine to be a DNS server. For that, we need to open port 53 for both the TCP and UDP protocols. Sudo IP tables -a input -p TCP -d port 53 -j accept. Sudo IP tables -a input -p UDP /d port 53 -j accept. Finally, we have an almost complete usable rule set for our input chain. Sudo IP tables -l chain input policy accept target prot opt or source destination accept or anywhere CT state. Related established accept TCP anywhere TCP DPT SSH drop or anywhere chain forward policy accept target prot opt source destination chain output policy accept target prot opt source destination donny at ubuntu /donaldson. However, this is only almost complete because there's still one little thing that we forgot. That is, we need to allow traffic for the loopback interface. This is okay, because it gives us a good chance to see how to insert a rule where we want it if we don't want it at the end. In this case, we'll insert the rule at input 1, which is the first position of the input chain. Sudo IP tables -i input 1 -i lo -j accept. Tip. Before you inserted the accept rule for the LO interface, you might have noticed that sudo commands were taking a long time to complete and that you were getting sudo unable to resolve host. Resource temporarily unavailable messages. That's because sudo needs to know the machine host name so it can know which rules are allowed to run on a particular machine. It uses the loopback interface to help solve the host name. If the LO interface is blocked, it takes longer for sudo to resolve the hostname. Our rule set now looks like this. Sudo IP tables -l. Now, note how port 53 is listed as the domain port. To see port numbers instead of port names, we can use the -n switch. Sudo IP tables -l -n. Now, as things currently stand, we're still allowing everything to get through because we still haven't created a rule that blocks what we haven't specifically allowed. Before we do that though, let's look at a few more things that might want to allow. Blocking ICMP with IP tables. The conventional wisdom that you may have heard for most of your career is that we need to block all the packets from the Internet Control Message Protocol, ICMP. The idea you may have been told is to make your server invisible to hackers by blocking ping packets. Of course, there are some vulnerabilities that are associated with ICMP, such as the following. By using a botnet, a hacker could inundate your server with ping packets from multiple sources at once, exhausting your server's ability to cope. Certain vulnerabilities that are associated with the ICMP protocol can allow a hacker to either gain administrative privilege on your system, redirect your traffic to a malicious server, or crash your operating system. By using some simple hacking tools, someone could embed sensitive data in the data field of an ICMP packet in order to secretly exfiltrate it from your organization. However, while blocking certain types of ICMP packages is good, blocking all ICMP packages is bad. The harsh reality is that certain types of ICMP messages are necessary for the proper functionality of the network. Since the drop all that's not allowed rule that we'll eventually create also blocks ICMP packets, we'll need to create some rules that allow the types of ICMP packets messages that we have to have. So here it goes. Sudo IP tables -a input -m contract -p ICMP ICMP type 3 11 12 -ct state new established related -j accept. Here's the breakdown. -m contract. As before, we're using the contract module to allow packets that are in a certain state. This time though, instead of just allowing packets from the host to which our server has been connected, established, related, we're also allowing new packets that other hosts are sending to our server. -p ICMP. This refers to the ICMP protocol. -ICMP type. There are quite a few types of ICMP messages, which we'll outline next. Here are the three types of ICMP messages that we want to allow. Type 3. These are the destination unreachable messages. Not only can they tell your server that it can't reach a certain host, but they can also tell it why. For example, if the server has sent out a packet that's too large for a network switch to handle, the switch will send back an ICMP message that tells the server to fragment that large packet. Without the ICMP, the server would have connectivity problems every time it tries to send out a large package that needs to be broken up into fragments. Type 11. Time exceeded messages. Let your server know that the packet that it has sent out has either exceeded its time to live (TTL) value before it could reach its destination, or that a fragmented packet couldn't be reassembled before the TTL expiration date. Type 12. Parameter problem messages indicate that the server had sent a packet with a bad IP header. In other words, the IP header is either missing an option flag or it's of an invalid length. Three common message types are conspicuously absent from our list. Type 0 and Type A. These are the infamous ping packets. Actually, Type 8 is the echo request packet that you want to send out to ping a host, while Type 0 is the echo reply that the host would return to let you know that it's still alive. Of course, allowing ping packets to get through could be a big help in troubleshooting network problems. If that scenario ever comes up, you could just add a couple of IP table rules to temporarily allow pings. Type 5. Now, we have the infamous redirect messages. Allowing these could be handy if you have a router that can suggest more efficient paths to the server to use, but hackers can also use them to redirect you to some place that you don't want to go. So just block them. There are lots more ICMP message types that I've shown here, but these are the only ones that we need to worry about for now. When we use sudo IP tables-l, we'll see our new rule set as things currently stand. Looks good, huh? Well, not really. We haven't blocked anything with this rule set yet, so let's take care of that. Blocking everything that isn't allowed with IP tables. To start blocking stuff that we don't want, we have to do one of two things. We can set a default drop or reject policy for the input chain, or we can leave the policy set to accept and create a drop or reject rule at the end of the input chain. Which one you choose is really a matter of preference. course, before you choose one over the other, you might want to check your organization's policy manual to see if your employer has a preference. The difference between drop and reject is that drop blocks packets without sending any message back to the sender. Reject blocks packets and then sends a message back to the sender about why the packets were blocked. For our present purposes, let's say that we just want to drop packages that we don't want to get through. Tip. There are times when drop is better and times when reject is better. Use drop if it's important to make your host invisible, although even that isn't that effective, because there are other ways to discover hosts. If you need your host to inform other hosts about why they can't make a connection, then use reject. The big advantage of reject is that it will let connecting hosts know that their packets are being blocked so that they will know how to immediately quit trying to make a connection. With drop, the host that's trying to make the connection will just keep trying to make the connection until it times out. To create a drop rule at the end of the input chain, use this command, sudo iptables-a input-j drop. To set the default drop policy instead, we can use this command, sudo iptables-p input drop. The big advantage of setting up a default drop or reject policy is that it makes it easier to add new accept rules if needed to be.
This is because if we decide to keep the default accept policy and create a drop or reject rule instead, that rule has to be at the bottom of the list. Since IP tables rules are processed in order from top to bottom, any accept rules that come after that drop or reject rule would have no effect. You would need to insert any new accept rules above that final drop or reject rule, which is just a tiny bit less convenient than just being able to append them to the end of the list. For now, in order to illustrate my next point, I've just left the default accept policy and added the drop rule. When we look at our new rule set, we'll see something that's rather strange. Sudo iptables-l. The first rule and the last rule of the input chain look the same, except that one is a drop and the other is an accept. Let's look at it again with the -v verbose option, sudo iptables-l-v. Now we can see that LO for loopback shows up under the in column of the first row, and that N shows up under the in column of the last row. We can also see that the -v switch shows the number of packets and bytes that have been counted by each row. So, in the preceding example, we can see that the CT state related established rule has accepted 828 packets and 52,354 bytes. The drop all rule has blocked 251 packets and 40,763 bytes. This all looks great, except that if we were to reboot the machine right now, the rules would disappear. The final thing that we need to do is make them permanent. There are several ways to do this, but the simplest way to do this on an Ubuntu machine is to install the iptables persistence package. Sudo apt install iptables-persistent. During the installation process, you'll be presented with two screens that ask you whether you want to save the current set of iptables rules. The first screen will be for IPv4 tables, while the second will be for IPv6 rules. Figure 4.1, configuring iptables persistent on Ubuntu. You'll now see two new tables files in the etc iptables directory. ls-l etc iptables star. If you were to reboot the machine now, you'd see that your iptables rules are still there and in effect. The only slight problem with iptables persistent is that it won't save any subsequent changes that you make to the rules. That's okay though. I'll show you how to deal with that in just a bit. Hands-on lab for basic iptables usage. You'll complete this lab on your Ubuntu 20.04 virtual machine. Follow these steps to get started. Shut down your Ubuntu virtual machine and create a snapshot. After you boot it back up, look at your IP tables rules, or lack thereof, by using this command, sudo iptables-l. With our default Ubuntu setup, the uncomplicated firewall UFW service is already running, albeit with an unactivated firewall configuration. We want to disable it to work directly with IP tables. Do that now with this command, sudo systemctl disable --now UFW. Create the rules that you need for a basic firewall, allowing for secure shell access, DNS queries and zone transfers, and the proper types of ICMP. Deny everything else. Use this command to view the results, sudo iptables-L. Oops, it looks like you forgot about that loopback interface. Add a rule for it at the top of the list, sudo iptables-I input1-ILO-J accept. View the results by using the following two commands. Note the difference between the output of each. Sudo iptables-L sudo iptables-L-v. Install the iptables-persistent package and choose to save the IPv4 and IPv6 rules when prompted. Sudo apt install iptables persistent. Reboot the virtual machine and verify that your rules are still active. Keep this virtual machine. You'll be adding more to it in the next hands-on lab. That's the end of this lab. Congratulations. Blocking invalid packets and with IP tables. If you've been in the IT business for any length of time, you're most likely familiar with the good old TCP three-way handshake. If you're not, no worries, here's the simplified explanation. Let's say that you're sitting at your workstation and you pull up a Fireworks to visit a website. To access that website, your workstation and the web server have to set up the connection. Here's what happens. Your workstation sends a packet with only the SYN flag set to the web server. This is your workstation's way of saying, "Hello, Mr. Server, I'd like to make a connection with you." After receiving your workstation's SYN packet, the web server sends back a packet with the SYN and ACK flags set. With this, the server is saying, "Yeah, bro, I'm here and I'm wanting to connect with you." Upon receiving of the SYN ACK packet, the workstation sets back a packet with only the ACK flag set. With this, the workstation is saying, "Cool deal, dude, I'm glad to connect with you." Upon receipt of the ACK packet, the server sets up the connection with the workstation so that they can exchange information. This sequence works the same way for setting up any kind of TCP connection. This includes connections that involve secure shell, telnet, and various mail server protocols, among other things. However, clever people that use a variety of tools to craft TCP packets with some very, very weird combination of flags. With these so-called invalid packets, there are a few things could happen. The invalid packets could be used to elicit responses from the target machine in order to find out what operating system is running, what services are running on it, and which versions of the services are running. The invalid packets could be used to trigger certain sorts of security vulnerabilities on the target machine. Some of these invalid packets require more processing power than what normal packets require, which would make them useful for performing denial-of-service attacks. Now, in truth, the drop all rule at the end of the filter table's input chain will block some of these invalid packets. However, there are some things that this rule might miss, and even if we could count on it to block all the invalid stuff, this still isn't the most efficient way of doing things. By depending on this drop all rule, we're allowing these invalid packets to travel through the entire input chain, looking for rules that will let them through. When no allow rule is found for them, they'll finally get blocked by the drop all rule, which is the last rule in the chain. So what if we could find a more efficient solution? Ideally, we'd like to block these invalid packets before they travel through the entire input chain. We could do that with a pre-routing chain, but the filter table doesn't have a pre-routing chain. Therefore, we need to use the pre-routing chain of the mangle table instead. Let's start by adding these two rules. Sudo iptables-t mangle-a pre-routing-m contract -ct state invalid-j drop. sudo IP tables -t mangle -a pre-routing -p TCP !sin -m contract -ct state new -a j drop. The first of these rules will block most of what we would consider invalid. However, there are still some things that it misses. Due to this, we added the second rule, which blocks all new packets that are not SYN packets. Now, let's see what we have. Sudo IP tables -l. We can't see any rules, can we? That's because by default, IP tables -l only shows rules for the filter table. We need to see what we just placed in the mangle table, so let's do this instead. Sudo IP tables -t. Here, we use the -t mangle option to indicate that we want to see the configuration for the mangle table. Something rather curious that you may have noticed is how IP tables renders the rule that was created by the sudo IP tables -t mangle a pre-routing p TCP SYN m contract tt state new j drop command. For some reason, it renders like this. Drop TCP -- anywhere TCP flags fin SYN rest axin ct state new. It looks strange, but don't let that throw to you. It still means that it's blocking new packets that aren't sync packets. Previously, I mentioned that the IP table's persistent packet won't save subsequent changes to IP table rules. So, as things stand now, the mangle table rules that we just added will disappear once I rebooted this virtual machine. To make these changes permanent, I'll use the IP table save command to save a new file in my own home directory. Then, I'll copy the file over to the ACT IP tables directory, replacing the original one. Sudo IP tables -save > rules.v4. Sudo cp rules v4 -etc -ip tables. To test this, we'll use a handy utility called nmap. It's a free utility that you can install on your Windows, Mac or Linux workstation. Or if you don't want to install it on your host machine, you can install it on one of your Linux virtual machines. It's in the normal repositories of Debian, Ubuntu, Red Hat Enterprise Linux 727 and Red Hat Enterprise Linux or Linux 8. So just install the nmap package with the appropriate install command for your distro. If you want to install nmap on a Windows or Mac host machine, you'll need to download it from the nmap website. You can download nmap from the official website, which can be found here, nmap.org/download.html. With our new mangle table rules in place, let's perform an Xmax scan of our Ubuntu machine. I have nmap installed here on the Fedora workstation that I'm currently using, so I'll just use this for now. I can do this like so. Sudo nmap -sx 192.168.0.15. By default, nmap only scans the most commonly used 1000 port. The Xmax scan sends invalid packets that consist of the fin, PSH, and ERG flags. The fact that all 1000 scanned ports show as open filter means that the scanner was blocked and that nmap can't determine the true state of the port. In reality, port 22 is open. We can view the result to see which rule did the blocking. To simplify things a bit, I only show the output for the pre-routing chain since it's the only mangle table chain that's doing anything. Sudo IP tables -t mangle -l-v. Here you can see that the first rule, the invalid rule, blocked 2000 packages and 80,000 bytes. Now let's zero out the counter so that we can do another scan. Sudo IP tables -t mangle -z. Sudo IP tables -t mangle -l-v. This time, let's do a Windows scan which bombards the target machine with ACK packets. Sudo nmap -sw 192.168.0.15. As before, the scan was blocked, as indicated by the message of that all 1000 scanned ports have been filtered. Now let's view what we have on the target Ubuntu machine. Sudo IP tables -t mangle -l-v. This time we can see that our invalid packets got past the first rule, but were blocked by the second rule. Now just for fun, let's clear out the mangle table rules and do our scans again. We'll use the -d option to delete the two rules from mangle table. sudo iptables-t mangle-d pre-routing 1, sudo iptables-t mangle-d pre-routing 1. When you delete a rule, you have to specify the rule number just like you do when you insert a rule. Here, I've specified the rule 1 twice, because deleting the first rule moved the second rule up to the first place. Now let's verify that the rules are gone. Sudo iptables-t mangle-l. Yeah, they are. Cool. Now let's see what we get when we perform another Xmas scan. Sudo nmap-sx 192.168.0.15. Even without the mangle table rules, it shows that my scan is still blocked. What's up with that? This is happening because I still have the drop all rule at the end of the input table. Let's disable that and see what we get with another scan. First, I need to see what the rule number is. Sudo iptables-l. Counting down, I can see that it's the rule number 4, so I'll delete it. Sudo iptables-d input 4. Sudo iptables-lc. Now for the Xmas scan, sudo nmap-sx 192.168.0.15. This time the scan shows that 999 ports are closed and that port 22, the SSH port, is either opened or filtered. This shows that the scan is no longer being blocked by anything, restoring the deleted rules. When I use the iptables-d commands, I only deleted the rules from the runtime configuration, not from the rules.v4 configuration file. To restore the rules that I deleted, I can either reboot the machine or restart the netfilter persistent service. The later choice is quicker, so I activate it like this. Sudo systemctl restart netfilter persistent. The iptables-l and iptables-t mangle-l commands will show that all the rules are now back in effect. Hands-on lab for blocking invalid IPv4 packets. For this lab, you'll use the same virtual machine that you used for the previous lab. You won't replace any of the rules that you already have. Rather, you'll just add a couple. Let's get started. Look at the rules for the filter and the mangle tables. Note that the -v option shows you statistics about packets that were blocked by the drop and reject rules. Then, zero out the blocked packets counter. Sudo iptables-l-v, sudo iptables-t mangle-l-v, sudo iptables-z, sudo iptables-t mangle-z. From either your host machine or another virtual machine, perform the null and Windows nmap scans against the virtual machine. Sudo nmap-sn, IP address of your own VM, sudo nmap-sw, IP address of your own virtual machine. Repeat step 1, you should see a large jump in the number of packets that were blocked by the final drop rule in the input chain of the filter table. Sudo iptables-l-v, sudo iptables-t mangle-l-v. Make the firewall work more efficiently by using the pre-routing chain of the mangle table to drop invalid packets, such as those that are produced by the 2 nmap scans that we just performed. Add the 2 required rules with the following 2 commands. Sudo iptables-t mangle-a pre-routing-m contracts/ct state invalid -a drop sudo iptables-t mangle-a pre-routing-p tcp exclamation mark -sin-m contracts/ct state new-j drop. Save the new configuration to your own home directory, then copy the file to its proper location and zero out the blocked packet counters. Sudo iptables save created and signed rules.v4, sudo copy rules.v4 ect iptables sudo iptables-z sudo iptables-t mangle-z. Perform only the null scan against the virtual machine. Sudo nmap-n IP address of your own virtual machine. Look at the IP table rule set and observe which rule was triggered by the nmap scan. Sudo iptables-l-v, sudo iptables-t mangle-l-v. This time perform just the Windows scan against the virtual machine. Sudo nmap-sw, IP address of your own virtual machine. Observe which rule was triggered by this scan. Sudo iptables-l-v, sudo iptables-t mangle-l-v. That's the end of this lab. Congratulations. Protecting IPv6. I know. You're used to having all networking based on IPv4 with its nice, short, easy to use IP addresses. However, that can't last forever, considering that the world is now out of new IPv4 addresses. IPv6 offers a much larger address space that will last for a long time to come. Some organizations, especially wireless carriers, are either in the process of switching over to IPv6 or have already switched to it. So far, all we've covered is how to set up an IPv4 firewall with IP tables. But remember what we said before, with IP tables you need one daemon and one set of rules for the IPv4 network and another daemon and a set of rules for IPv6. This means that when using IP tables to set up a firewall, protecting IPv6 means doing everything twice. Most Linux distros come with IPv6 networking enabled by default, so you either need to protect it with a firewall or disable it. Otherwise, your IPv6 address will still be open for attack since you need the IPv4 firewall that you just configured to unprotect it. This is true even if your server or device is facing the IPv4 internet, because there are ways to tunnel IPv6 packets through an IPv4 network. Fortunately, the commands for setting up an IPv6 firewall are mostly the same as what we just covered. The biggest difference is that instead of using the IP tables command, you'll use the IP6 tables command. Let's start with our basic setup, just like we did for IPv4. Sudo IP6 tables -a input -ilo -j accept. Sudo IP6 tables -a input -m contract -ct state establish related -j accept. Sudo IP6 tables -a input -ptcp -d port ssh -j accept. Sudo IP6 tables -a input -ptcp -d port 53-j accept. Sudo IP6 tables -a input -pudp -d port 53-j accept. The other big difference between IPv4 and IPv6 is that with IPv6 you must allow more types of ICMP messages than you need to for IPv4. This is due to the following reasons. With IPv6, new types of ICMP messages have replaced the address resolution protocol ARP. With IPv6, dynamic IP address assignments are normally done by exchanging ICMP discovery messages with other hosts rather than by the HCP. With IPv6, echo request and echo replies, the infamous ping packets, are required when you need to tunnel IPv6 packets through an IPv4 network. And of course, we still need the same types of ICMP messages that we need for IPv4, so let's start with those. Sudo IP6 tables -a input -p ICMPv6 -ICMPv6 type 1 -j accept. Sudo IP6 tables -a input -p ICMPv6 -ICMPv6 type 2 -j accept. Sudo IP6 tables -a input -p ICMPv6 -ICMPv6 type 3 -j accept. Sudo IP6 tables -a input -p ICMPv6 -ICMPv6 type 4 -j accept. These message types are as follows in order of appearance: destination unreachable, packet is too big, time exceeded, parameter problem with the packet header. Next, we'll enable echo request type 128 and echo responses 129 so that IPv6 over IPv4 tunneling will work. Sudo IP6 tables -a input -p ICMPv6 -ICMPv6 type 128 -j accept. Sudo IP6 tables -a input -p ICMPv6 -ICMPv6 type 129 -j accept. The Teredo protocol is one of a few different ways to tunnel IPv6 packets across an IPv4 network. This protocol is what requires echo request and echo replies, the infamous ping packets, to be allowed through a firewall. However, if you search through your distro repositories for a Teredo package, you won't find it. That's because the Linux implementation of the Teredo package protocol is called Mirado. So when installing the Teredo protocol on a Linux machine, you'll need to install the Mirado and Mirado server packages. The next four ICMP message types that we need are for the link local multicast receiver notification messages. Sudo IP6 tables -a input -protocol ICMPv6 ICMPv6 type 130. Sudo IP6 tables -a input -protocol ICMPv6 ICMPv6 type 131.
sudo ip6 tables-a input-protocol icmpv6-icmpv6-type 132, sudo ip6 tables-a input-protocol icmpv6-icmpv6-type 143. These are as follows in order of appearance: listener query, listener report, listener done, listener report v2. Next up are our neighbor and router discovery message types. Sudo ip6 tables-a input-p icmpv6-icmpv6-type 134-j accept, sudo ip6 tables-a input-p icmpv6-icmpv6-type 135-j accept, sudo ip6 tables-a input-p icmpv6-icmpv6-type 136-j accept, sudo ip6 tables-a input-p icmpv6-icmpv6-type 141-j accept, sudo ip6 tables-a input-p icmpv6-icmpv6-type 142-j accept. These are as follows in order of appearance: router solicitation, router advertisement, neighbor solicitation, neighbor advertisement, inverse neighbor discovery solicitation, inverse neighbor discovery advertisement. Space doesn't permit me to go into the details of these message types, so for now, let's just say that they're required in order for IPv6 hosts to dynamically assign themselves an IPv6 address. For times when you're using security certificates to authenticate the routers that are attached to your network, you also need to allow secure neighbor discovery send messages. Sudo ip6 tables-a input-p icmpv6-icmpv6-type 148-j accept, sudo ip6 tables-a input-p icmpv6-icmpv6-type 149-j accept. Are your fingers tired yet? If so, have no fear. This next group of ICMP rules is the last one. This time, we need to allow multicast router discovery messages. Sudo ip6 tables-a input-p icmpv6-icmpv6-type 151-j accept, sudo ip6 tables-a input-p icmpv6-icmpv6-type 152-j accept, sudo ip6 tables-a input-p icmpv6-icmpv6-type 153-j accept. Finally, we'll add our drop rule to block everything else. Sudo ip6 tables-a input-g drop. I know you're thinking, whoa, that's a lot of hoops to jump through just to set up a basic firewall. And yeah, you're right, especially when you also need to configure rules for IPv6. Soon, I'll show you what the Ubuntu fork came up with to make things simpler. You can get the whole scoop on how to use IP tables on Ubuntu here, help.ubuntu.com/community/iptables-how-to. Hands-on lab for IP6 tables. For this lab, you'll use the same Ubuntu virtual machine that you used in the previous IP table labs. You leave the IPv4 firewall setup that's already there as is and create a new firewall for IPv6. Let's get started. View your IPv6 rules, or lack thereof, with this command, sudo ip6 tables-l. Create the IPv6 firewall. Due to formatting constraints, I can't list the entire code block of commands here. You can find the respective commands in the scripts directory in the code file that you can download from the Pact Publishing website. View the new rule set by using the following command, sudo ip6 tables-l. Next, set up the mangle table rules for blocking invalid packets. Sudo ip6 tables-t-mangle-a pre-routing-m contract-ct state invalid-j drop, sudo ip6 tables-t-mangle-a pre-routing-ptcp !sin-m contract-ct state new-j drop. Save the new rule set to a file in your own home directory and then transfer the rules file to the proper location. Sudo ip6 tables-save created and signed rules.v6 sudo cp rules.v6-etc-ip tables. Obtain the IPv6 address of the virtual machine with this command, IP-A. On the machine on which you installed nmap, perform a Windows scan of the virtual machine's IPv6 address. The command will look like this, except with your own IP address. Sudo nmap-6-sw fe80 column A00 column 27FF column FE9F column D923. On the virtual machine, observe which rule was triggered with this command, sudo ip6 table/d-mangle-l-b. You should see non-zero numbers for the packet counter for one of the rules. On the machine on which you installed nmap, perform an xmax scan of the virtual machine's IPv6 address. The command will look like this, except with your own IP address. Sudo nmap-6-sx IPv6 address. As before on the virtual machine, observe which rule was triggered by this scan. Sudo ip6 table/t-mangle-l-b. Shut down the virtual machine and restore it from the snapshots that you created at the beginning of the hands-on lab for basic IP tables usage section. That's the end of this lab. Congratulations. So far you've seen the good, the bad and the ugly of IP tables. It's very flexible and there's a lot of power in the IP tables commands. If you're clever at shell scripting, you can create some rather complex shell scripts that you can use to deploy firewalls on machines all across your network. On the other hand, setting everything right can be quite complex, especially if you need to consider that your machines have to run both IPv4 and IPv6, and that everything you do for IPv4 has to be done again for IPv6. If you're a masochist, you might actually enjoy it. NF tables, a more universal type of firewall system. Now let's turn our attention to NF tables, the new kid on the block. So, what does NF tables bring to the table? Yes, the pun was intended. You can forget about needing separate daemons and utilities for all of the different networking components. The functionality of IP tables, IP6 tables, EB tables, and ARP tables is now all combined in one neat package. The NFT utility is now the only firewall utility that you'll need. With NFT tables, you can create multi-dimensional trees to display your rule sets. This makes troubleshooting vastly easier because it's now easier to trace a packet all the way through all of the rules. With IP tables, you have to filter, NAT, mangle, and security tables installed by default whether or not you use each one. With NF tables, you only create the tables that you intend to use, resulting in enhanced performance. Unlike IP tables, you can specify multiple actions in one row instead of having to create multiple rules for each action. Unlike IP tables, new rules get added atomically. That's a fancy way of saying that there's no longer a need to reload the entire rule set in order to just add one rule. NF tables has its own built-in scripting engine, allowing you to write scripts that are more efficient and more human-readable. If you already have lots of IP table scripts that you still need to use, you can install a set of utilities that will help you convert them to the NF tables format. That is, unless you're running Ubuntu 22.04, which can automatically translate IP table commands for you. Although NF tables was created by Red Hat, Ubuntu was the first enterprise-grade Linux distro to offer it as an option, beginning with Ubuntu 16.4. It's now the default option for Ubuntu 22.04, SUSE, OpenSUSE, and the RHEL 8.9 type distros. Let's begin by looking at some basic NF table concepts. Learning about NF tables and chains. If you're used to IP tables, you might recognize some of the NF tables terminology. The only problem is that some of the terms are used in different ways, with different meanings. Let's go over some examples so that you'll know what I'm talking about. Tables. Tables in NF tables refer to a particular protocol family. The table types are IP, IP6, INET, ARP, Bridge, and NetApp. Chains. Chains in NF tables roughly equate to tables in IP tables. For example, in NF tables you could have filter, root, or NAT chains. Getting started with NF tables. Let's start with a clean snapshot of our Ubuntu 22.04 virtual machine since it comes with NF tables already installed. Tip: you can use Ubuntu 20.04 if you really want to, But you'll first have to install nftables by doing sudo apt install nftables. Now let's take a look at the list of installed tables. A sudo nft list tables. You didn't see any tables, did you? So let's load some up. Configuring nftables in Ubuntu. On the Ubuntu virtual machine that we'll be using, the default nftables.conf file is nothing more than a meaningless placeholder. The file you need, which you will copy over to replace the default nftables.conf file, is elsewhere. Let's check it out. First, we'll go into the directory where the sample configurations are stored and list the sample configuration files. cd usr share doc nftables examples ls-l. You should see something similar to this. If you view the contents of the workstation.nft file, you'll see that it's the one we need. Next, we'll copy the workstation file over to the etc directory, changing its name to nftables.conf. Note that this will overwrite the old nftables.conf file, which is what we want. Sudo cp workstation.nft-etc-nftables.conf. Here's a breakdown of what you'll see in the etc-nft-tables.conf file that you'll be using. # user sbin nft-f. Although you can create normal bash shell scripts with nftable commands, it's better to use the built-in scripting engine that's included with nftables. That way, we can make our scripts more human readable and we don't have to type nft in front of everything you want to execute. Flush rule set. We want to start with a clean slate, so we'll flush out any rules that may have already been loaded. Table init filter. This creates an init family filter which works for both IPv4 and IPv6. The name of this table is filter, but could just as well have been something a bit more descriptive. Chain input. Within the first pair of curly brackets, we have a chain called input. Again, the name could have been something more descriptive. Type filter hook input priority 0. Within the next pair of curly brackets, we define our chain and list the rules. This chain is defined as a filter type. Hook input indicates that this chain is meant to process incoming packets. Because this chain has both a hook and a priority, it will accept packets directly from the network stack. Finally, we have the standard rules for very basic host firewall, starting with the input interface IIF rule, which allows the loopback interface to accept packets. Next is the standard connection tracking CT rule, which accepts traffic that's in response to a connection request from this host. Then there's a commented add rule to accept secure shell in both secure and non-secure web traffic. CT state new indicates that the firewall will allow other hosts to initiate connections to our server on these ports. The meta and fproto IPv6 rule accepts neighbor discovery packets, allowing IPv6 functionality. The counter drop rule at the end silently blocks all other traffic and counts both the number of packets and the number of bytes that it blocks. This is an example of how you can have one nftables rule perform multiple different actions. If all you need on your Ubuntu server is a basic no-frills firewall, your best bet is just to edit this atc nftables.conf file so that it suits your own needs. For starters, let's set this up to match the setup that we created for the IP table section. In other words, let's say that this is a DNS server and we need to allow connections to port 22 and port 53. Remove the comment symbol from in front of the TCP dport lane, get rid of port 80 and 443 and port 53. The line should now look like this. TCP dport 2253 CT state new accept. Note how you can use nftable rules to open multiple ports. DNS also uses port 53 UDP, so let's add a line for it. UDP dport 53 CT state new accept. When you're only opening one port, you don't need to enclose that port number within curly brackets. When opening multiple ports, just include the comma-separated list within curly brackets, with a blank space after each comma before the first element and after the last element. Load the configuration file and view the results. Sudo systemctl reload nftables. Sudo nft list rule set table inet filter. The counter drop rule is another example of how an nftables rules can do multiple things. In this case, the rule drops and counts unwanted packets. So far, the rule has blocked 1 packet and 32 bytes. To demonstrate how this works, let's say that we want to make a log entry when packets are dropped. Just add the log keyword to the drop rule, like so. Counter log drop. To make these messages easier to find, add a tag to each log message, like this. Counter log prefix drop packet drop. Now, when you need to peruse the varlog curlog file to see how many drop packets you've had, just search for the drop package text string. Now, let's say that we want to block certain IP addresses from reaching the secure shell port of this machine. To do this, we can edit the file, placing a drop rule above the rule that opens port 22. The relevant section of the file will look like this. After we reload the file, we'll be blocking SSH access from 2 different IPv4 addresses. Any attempts to log in from either of those 2 addresses will create a varlog curlog message with the blocked SSH packets tag. Note that we place the drop rule ahead of the accept rule because if the accept rule gets read first, the drop rule won't have an effect. Next, we need to allow the desired types of ICMP packets like so. In this case, you need to separate rules for ICMPv4 and ICMPv6. Finally, we'll block invalid packets by adding a new pre-routing chain to the filter table, like so. Now we can save the file and close the text editor. Due to formatting constraints, I can't show the entire completed file here. To see the whole file, download the code from the packed website and look in the chapter 4 directory. The example file you seek is the nftables_example_1.com file. Now let's load up the new rules. Sudo systemctl reload nftables. Another really cool thing to note is how we mixed IPv4 IP rules with IPv6 IP6 rules in the same configuration file. Also, unless we specify otherwise, all the rules that we create will apply to both IPv4 and IPv6. That's the beauty of using an innet type table. For simplicity and flexibility, you'll want to use inet tables as much as possible rather than separate file tables for IPv4 and IPv6. Most of the time, when all you need is just a simple host variable, your best bet would be to just use this nftables.conf file as your starting point and edit the file to suit your own needs. However, there's also a command line component you may find useful using nft commands. My preferred method of working with nftables is just to start with a template and hand edit it to my liking as we did in the previous section, but for those who'd rather do everything from the command line, there's the nft utility. Tip: even if you know that you'll always create firewalls by hand editing nftables.conf, there's still a couple of practical reasons to know about the nft utility. Let's say that you've just observed an attack in progress and you need to stop it quickly without bringing down the system. With an nft command, you can create a custom rule on the fly that will block the attack. Creating tables rules on the fly will also allows you to test the firewall as you configure it before making any permanent changes. And if you decide to take a Linux security certification exam, you might see questions about nft commands. I happen to know. There are 2 ways to use the nft utility. For one, you could just do everything directly from the bash shell, prefacing every action you want to perform with nft, followed by the nft subcommands. The other way is to use nft in the interactive mode. For our present purposes, we'll just go with the bash shell. First, let's delete our previous configuration and create an inet table since we want something that works for both IPv4 and IPv6. We want to give it a somewhat descriptive name, so let's call it Ubuntu_filter. Sudo nft delete table inet filter sudo nft list tables. Sudo nft add table inet Ubuntu_filter sudo nft list tables. Next, we'll add an input filter chain to the table that we just created. Note that since we're doing this from the bash shell, we need to escape the semicolon with a backslash. Sudo nft add chain inet Ubuntu_filter input. Type filter hook input priority 0 policy drop. We could have given it a more descriptive name, but for now input works. Within the pair of curly brackets, we're setting the parameters for this chain. Each nftable's protocol family has its own set of hooks, which define how the packet will be processed. For now, we're only concerned with the IP6, INET families, which have the following hooks. Pre-routing, input forward, output post-routing. Of these, we're only concerned with the input and output hooks, which apply to filter type chains. By specifying a hook and a priority to our input chain, we're saying that we want this chain to be a base chain that will accept packets directly from the network stack. You will also see that certain parameters may be terminated by semicolon, which in turn would need to be escaped with a backslash if you're running the commands from the bash shell. Finally, we're specifying a default policy of drop. If we had not specified a drop as a default policy, then the policy will have been accept by default. Tip: every NFT command that you enter takes effect immediately. So if you're doing this remotely, you'll drop your secure shell connection as soon as you create a filter chain with a default drop policy. Some people like to create chains with a default accept policy and then add a drop rule as the final rule. Other people like to create chains with a default drop policy and then leave off the drop rule at the end. Be sure to check your local procedures to see what your organization prefers. Verify that the chain has been added. You should see something like this. Sudo NFT list table inet ubuntu underscore filter. That's great, but we still need some rules. Let's start with a connection tracking rule and a rule to open a secure shell port. Then we'll verify that they were added. Sudo nft add rule inet ubuntu underscore filter input ct state established accept sudo nft add rule inet ubuntu underscore filter input tcp dport 22 ct state new accept sudo nft list table inet ubuntu underscore filter table inet ubuntu underscore filter chain input type filter hook input priority 0 policy drop ct state established accept tcp dport ssh state new accept. Okay, that looks good. You now have a basic working firewall that allows secure shell connections. Well, except that just as we did in the IP table section of this chapter, we forgot to create a rule that allowed the loop packet actor to accept packets. Since we want this row to be at the top of the rules list, we'll use insert instead of add. Sudo nft insert row inet ubuntu underscore filter ubuntu iif lo accept sudo nft list table inet underscore ubuntu underscore filter table inet ubuntu underscore filter chain input type filter hook input priority 0 policy drop iif lo accept ct state established accept tcp dport ssh ct state new accept. Now we're all set. But what if you want to insert a rule at a specific location? For that you'll need to use list with the -a option to see the rule handles. Sudo nft list table inet ubuntu underscore filter -a table inet ubuntu underscore filter chain input type filter hook input priority 0 policy drop iif lo accept handle for ct hash handle for ct state established accept hash handle 2 tcp dport ssh ct state new accept hash handle 3. As you can see, there's no real rhyme or reason for the way the handles are numbered. Let's say that we want to insert the rule about blocking certain IP addresses from accessing the secure shell port. We can see that the SSH accept rule is handle 3. So we'll need to insert our drop rule before it. This command will look like this. So to place the rule before the rule with the handle 3 label, we have to insert it at position 3. The new rule that we just inserted has the label handle 6. To delete a rule, we have to specify the rule's handler number. As is the case with IP tables, everything you do from the command line will disappear once you reboot the machine. To make it permanent, let's redirect the output of the list subcommand to the nftables.conf configuration file. Of course, we'll want to have made a backup copy of the already existing file in case we want to revert back to it. Sudo sh-c nft list table inet ubuntu underscore filter greater than etc nftables.conf. Due to a quirk in the bash shell, we can't just redirect output to a file in the etc directory in the normal manner, even when we use sudo. That's why I had to add the sh-c command with the nft list command surrounded by double quotes. Also note that the file has to be named nftables.conf because that's what the nftable system said it looks for. Now when we look at the file, we'll see that there are a couple of things that are missing. Those of you who are sharp-eyed we'll see that we're missing the flush rule and the shebang line to specify the shell that we want to interpret the script. Let's add them. Much better. Let's test this by loading the new configuration and observing the list output. That's all there is to create your all simple host firewall. Of course, running commands from the command line rather than just creating a script file in your text editor does make for a lot more typing. However, it does allow you to test your rules on the fly as you create them. And creating your configuration in this manner and then redirecting the list output to your new configuration file relieves you of the burden of having to keep track of all those curly brackets as you try to hand edit the file. It's also possible to take all of the NFT commands that we just created and place them into a regular old-fashioned bash shell script. Trust me though, you really don't want to do that. Just use the NF native scripting format as we've done here, and you'll have a script that performs better and is much more human readable. Hands-on lab for NF tables on Ubuntu. For this lab, you'll need a clean snapshot of your Ubuntu 22.04 virtual machine. Let's get started. Restore your Ubuntu virtual machine to a clean snapshot to clear out any firewall configurations that you created previously, or if you prefer, start with a new virtual machine. Disable UFW and verify that no firewall rules are present. Sudo systemctl disable --now UFW sudo IP tables.shell. You should see no rules listed for NF tables. Copy the workstation and NFT template over to the etc directory and rename it nftables.conf. Sudo copy, use, share, doc, nftables, examples, syntax workstation, etc nftables.com. Edit the etc nftables.com file to create your new configuration. Note that due to formatting constraints, I have to break this into 3 different code blocks. Make the top portion of the file look like this. Make the second portion of the file look like this. Make the final portion of the file look like this. Save the file and reload NF tables. View the results. From either your host computer or from another virtual machine, we do a Windows scan against the Ubuntu virtual machine. Look at the packet counters to see which blocking rule was triggered. Hint, it's in the pre-routing chain. Sudo nft list rules it. This time do a null scan of the virtual machine. Sudo nmap-sn IP address of the virtual machine. Finally look at which rule was triggered this time. Hint, it's the other one in the pre-routing chain. Sudo nft list rules it. In the varlook kernel.log file, search for the invalid packet string to view the messages about the dropped invalid packets. That's the end of this lab. Congratulations. In this section, we looked at the ins and outs of NF tables. We looked at ways to configure it to help prevent certain types of attacks. In the next chapter, we'll look at the helper programs for our helper programs. Summary. In this chapter, we looked at both of the helper programs that directly interface with the NetFilter firewall. First, we looked at our trusty old friend, IP tables. We saw that even though it's been around forever and still works, it does have some shortcomings. And then we worked with NF tables and saw that it has certain advantages over the old IP tables. In the space that's been allotted for this chapter, I've only been able to present the essentials that you need in order to set up basic host protection. However, this should be enough to get you started. In the next chapter, we'll look at UFW and Firewall D, which are helper programs for the 2 helper programs that we discussed in this chapter. I'll see you there. Questions. Which of the following statements is true? IP tables is the easiest firewall system to work with. With IP tables, any rule that you create applies to both IPv4 and IPv6. With IP tables, you have to create IPv6 rules separately from IPv4 rules. With NF tables, you have to create IPv6 rules separately from IPv4 rules. What is the official name of the Linux firewall? IP tables, UFW, NF tables, NetFilter. Which of the following statements about NF tables is false? With NF tables, rules are added atomically. With NF tables, a table refers to a particular protocol family. With NF tables, ports and their associated rules are bundled into zones. With NF tables, you can write scripts in either normal bash shell scripting or with the scripting engine that's built into NF tables. Which IP tables commands would show you how many packets have been dropped by a particular rule? Which NF tables command would you use to see how many packets have been dropped by a particular rule? In IP tables, which of the following targets would cause packets to be blocked without sending a notification back to the source? Stop, drop, reject, or block. Which of the following 6 choices are tables in IP tables? NetFilter, filter, manual security, IP table, NAT. Which firewall system loads its rules atomically? Further reading, 25 IP table
Tables network firewall examples, IPv6 how-to, recommendations for filtering ICMPv6 messages and firewalls, NFTables wiki, NFTables examples. Answers: 1C, 2D, 3C, 4 sudo iptables-l-v, 5 sudo NFT list rule sets, 6B, 7B, C, D, and F, 8 NF tables.